So you want to learn some physics, either because you really need to ace the next test, or are just interested in everything that has anime girls next to it, or you just want to see me try to explain quantum mechanics while somehow fitting in anime. But here we go. Anyway, let's start off with the classics. Classical mechanics, that is. And let's start off with Apple Guy. No, not the Belgian one. Yes, that one. Anyway, this is Isaac Newton, as you probably know, and he made some laws. Physical laws, that is. So let's look at them. First, an object will not move or not stop moving unless acted on by an outside force. So hollow purple won't stop moving unless some kind of thing stops it moving. And that thing is force. Force is just a push or pull on something, and is Newton's second law, being mass times acceleration. Mass being how much of something there is, and acceleration being how fast its speed is changing. So the more force put into the slap, the more acceleration the face will experience, and the faster it will go from a still face to one moving very fast. However, the face will also push back against the hand, being a kind of opposite force, which is the third law. Every action has an equal and opposite reaction. Another thing, this force has an arrow. This is called a vector, and it just describes what way and how fast something is moving. And this is what Accelerator uses in a certain magical railgun, by the way. Anyway, these movements can be described with some equations, the Suvat equations, or the equations of motion, invented by Cedric Gaspard Suvat. I'm not kidding, look it up. So if you ever wanted to know how fast you can run, or how fast Hollow Purple is in the show, these equations are what you use. Now, here's a question. If you shot a gun and dropped a bullet at the same time, which one would hit the ground first? Neither. They would hit it at the same time, because you can split the motion of the object into its horizontal and vertical components. And since they were both dropped from the same height, they would both hit the ground at the same time. Why? Because of gravity, of course. This was discovered by Isaac Newton again, with the apple falling on his head. Though according to the Petals of Reincarnation, it must have been a fucking massive apple. Anyway, he found out that all masses attract each other, even the smallest objects do, and wrote it down as this equation, saying that the further an object is away from another, the less attraction it feels. And it feels less and less the further it is away from the object, because of the inverse square law. And the bigger the object, the bigger the attraction as well. Anyway, if all objects feel attraction for one another, why are we not in one big clump at this center of the universe? Well, that's because most objects are all moving, and for us on Earth, we are technically moving in a straight line, but the attraction of the sun keeps us moving towards it, constantly changing our direction. This is called a centripetal force, and as we constantly move around, we actually moreover are constantly falling towards the sun, but constantly miss it, being in an elliptical orbit, which is practically what every orbit is. Anyway, now let's look at energy. So when Yuji is throwing hands, that obviously is transferring energy to his victims. How do you describe this energy? Well, there are two main types of energy, kinetic and potential energy. Kinetic energy is the energy an object has when it's moving. So as this volleyball moves, it has kinetic energy. Potential energy is stored energy that can be used. So when Bam is pushed off here, he has a ton of gravitational potential energy, which as he falls will be converted into kinetic energy until the exact moment he hits the ground, where all the potential energy has been converted into kinetic. And this is the conservation of energy, where the kinetic and potential energy before something happens is equal to the kinetic and potential energy after it, as energy cannot be created or destroyed, only converted into something else. Anyway, that push must have taken some work, no? Well, of course it did. Literally. Work is the measure of energy transfer over a distance when an object is moved. So here, Rachel applies a force over some small distance and transfers her energy. However, work is only applied when something actually moves. So here with Historia punching Levi, even though she transfers some energy to Levi in the punch, since he did not move, no work has been done on Levi. By the way, talking about him, isn't he just so hot? I mean, speaking attractively, yes, of course, but he is probably also quite warm temperature-wise. This is because the atoms that make him up have a tiny bit of kinetic energy, and that causes them to wiggle in place. And the more they wiggle, the hotter he gets. So temperature is just atoms having a party. However, remember how I said that energy has to be conserved? because if Levi is hot, that means he is also emitting energy through electromagnetic radiation and therefore getting colder until he reaches absolute zero. And this transition is called entropy. Entropy is the increase in disorder of energy. So as stuff happens and energy is transferred between things, some of it will be lost to entropy. So if you're having a good time with S-Death, most of the energy will be put into the movement, but some of it will be lost as heat energy through sweat or body temperature. So there is no way to have an 100% efficient system that uses all the energy perfectly, including with S-Death. And eventually, all the energy will slowly dissipate, slowly reaching absolute zero, and that energy will be lost through radiation, which is a form of light. Which brings us to the next topic. So you know light. It allows us to see, and one of its forms is radiation, or it's just a way to call how light moves. It's how you feel warmth emanating from fire. But that radiation needs a way to get from the warmth of the fire to your skin, and to do that, it uses waves. As the fire burns, the radiation emanates out in all directions, and when it hits your skin, it transfers some of that energy to your skin, making you feel warmer. You can also move the light around with reflection, where it bounces off a surface, diffraction, where it bends around a corner or a small opening, and interference, where it touches another light wave, and then they can either become more powerful, constructively interfering, or they can become weaker, destructively interfering. There are also multiple forms of light, all with different wavelengths. However, we can only see the tiniest sliver of it. Everything else is either too long for us to see or too short for us to see. These different wavelengths make up what is called the electromagnetic spectrum, and the shorter the wavelength is, the more powerful it is. That's why the doctor runs out of the room every X-ray, because it is an extremely powerful wave. But where did that X-ray come from? Well, they used electricity, of course. First, let's look at what makes up electricity. Here we have the electron, what a surprise, which is a charged particle. This charge is actually very similar to that of gravity, where it attracts, but it also reflects. Think of it like Gojo's red and blue. The blue is the electron. It wants to suck things closer to it as it has a negative charge. And red, which is a proton, pushes away because it has a positive charge. And hollow purple, since it does neither, is neutral, so think of it as a neutron. This is a really dumb analogy, but you can get the picture. Also, similar charged particles do not want to be next to each other, like at all. It's like two introverts meeting in public. Anyway, the flow of electrons in a conductor, so some kind of metal, is called a current. It is literally measured by how many electrons are moving through a single point in a given amount of time, measured in something called amps. Then there are also two other things involved with electricity, voltage and resistance. Together, they form Ohm's law. Voltage is what moves the electrons along, or it is just the potential difference between 2 points. So if this point is positively charged and this side is negatively charged, the electrons are going to want to move towards the positive, and the bigger the difference, the faster they want to move. And then resistance is literally just evil current. It just slows it down. However, you might notice that this electricity is quite similar to magnetism. The opposites attract each other, the positive and negative. Are they the same thing? Turns out, yes, they are the same thing. Initially discovered by Hans Christian Ørsted, electricity and magnetism are literally two sides of the same coin. If you have a current of electrons flowing through a wire, they will create an electric field around said wire. If you move a magnet next to or through a coil of wire, you will induce a current in the wire. And so too with a moving electric charge. As it is a moving charge, it will make a magnetic field, which in turn will make an electric field, which will make a magnetic field, and so on and so forth. And this is just an electromagnetic wave. This is also light, but don't worry about that right now. These are all described by just 4 equations called the Maxwell equations. However, these fields don't just affect each other, but the entire conductors encircling them. When a conductor with a flowing current is put into a magnetic field, it will experience a force perpendicular to that field. And if you move around the wires a bit, along with the magnets, you can make a motor that turns electrical energy into rotational mechanical energy. However, just like with all things, this one is also not 100% efficient, and not just from the heat produced from the current, but from some things called Faraday's and Lenz's law. Now, you probably don't want to know about these two, so let's just show what they discovered. Faraday discovered that when a conductor is exposed to a changing magnetic field, it will induce an electromagnetic force in the conductor. Simply put, a new current. However, according to Lenz's law, that flow of electrons will always oppose the movement of the magnet. So it'll push back on the magnet as it gets closer and will pull on it as it gets further away. Think of it like an isekai protagonist. When they first appear, all the girls don't want to know them, but as they travel past, they become infatuated and start trying to keep up with them. You are going to have to deal with these terrible analogies for the rest of this video, by the way. Anyway, I mentioned that the electromagnetic waves are actually light, which is true. However, we already know the speed of electricity and magnetism in space, or their permeability. So couldn't we use them to discover how fast light travels? Yes, we can, with it being exactly 299,792,458 meters per second exactly, no decimals. However, if we derived this speed from two constants, doesn't that mean that the speed of light has to be a constant? Believe so, said Albert Einstein, who is now an anime girl for some fucking reason. Anyway, she said that if light is constant, that means time has to be relative. So that means regardless of how fast you are traveling compared to a stationary person, the light will travel at the speed of light. However, because of this, that means that people traveling at different speeds experience time and distance differently. Time dilation. To demonstrate this easier, let's imagine you are trying to send a message to two people at the same time, and they are on either side of a train moving at half the speed of light. When you send that message to both of them, you will see them both receive it at the same time, because you are all on the train together. However, to another person standing outside the train, they will see the person at the back of the train receive their message first, as they are moving towards the point where the message was originally sent, while the other person is going away from it. That is time dilation, showing that two different people can experience the same events but in different times. This also works with length, where distances appear to get shorter and shorter the faster you go, until you are going at the speed of light, where you don't even experience length. From light's perspective, they are created, and then they are immediately at their destination. However, you will never be able to even reach the speed of light, because to get there, you would need an infinite amount of energy, according to these equations. So every character that travels somehow faster or equal to the speed of light has an infinite amount of energy, and by extension, power. So f*** you power scale, as Shinra Kusakabe can beat Gojo. Okay, so we've talked about everything in general physics except... So you know that atoms are made up of tiny smaller particles. That should be common knowledge, I'm hoping. Those are the proton, electron, and the neutron. The protons decide what element the atom is, while the neutron is used to make different versions of the element, or to make it more stable. And the electron is just whizzing around the atom in an orbit, which can also help it make it more stable or different in chemical reactions. However, some of these atoms are so big that the particles inside just can't stand being next to each other. It's like an anime convention. When it's a smaller event, only a few people will be there. It's nice. You get to have a good time and meet new people, walk around, stretch your legs. But if you dare go to Anime Expo, you will feel like a sardine in a fucking can. So they split apart, or change into a new particle. There are mainly three ways that particles can decay without outside interference. They can either emit an alpha particle, becoming less heavy. A neutron can emit an electron and an antineutrino, turning into a proton and becoming a heavier element. Or they can emit a gamma ray, which doesn't change it, it's just pent up energy from a previous reaction. Also, all of these radiations can kill you in one way or another. Enjoy. However, you are probably saying, but what happens inside of nuclear bombs? Because everything nuclear physics related is nuclear bombs. Well, that would be fusion and fission. Fission is when an external particle, typically a neutron, interacts with a larger particle, causing it to split into two lighter particles. And fusion is when the same thing happens, but they merge together into a bigger particle instead. And both of these interactions produce a massive amount of energy, especially fusion, because a tiny amount of mass is converted to energy during these reactions. And using the most famous equation in science, E equals mc squared, and calculating how many atoms are in like 1 gram of uranium, you can see that if all that mass was converted to energy, it would be quite fucking big. Okay, so you remember when I said that light was a wave? That was a fucking lie. It's actually a particle. And also a wave. At the same time. What's going on here? Well, fun fact. Albert Einstein's only Nobel Prize was not for relativity or gravity, but for something else, called the photoelectric effect, where when light shines on a piece of metal, some of the electrons get kicked off it. The reason being that some light is powerful enough to do so, to rip the electrons from their orbits. But it does not work as a wave. The light has to be a particle for this effect to work, and the energy the light carries can only come in specific amounts of a certain multiple, quantas. And the double slit experiment used to prove that light is a wave also proves that light is a particle, because if you measure which slit the light went through instead of just looking at what shape it makes just 2 lines instead of being an interference pattern. Just a fun side tangent here as well. Since both of these equations are for energy, that means you can equate them. And that means if you rearrange them, that means that all mass has a wavelength, even though it is really, really small. Anyway, just like with light, the orbits of electrons are also quantized, and electrons can only orbit at specific energy levels. And when these electrons drop down a level, they emit some light corresponding to the energy levels they dropped. That's how LEDs work, by the way. However, the orbits of the electrons aren't really orbits, they're more clouds. It's like a fog. The electron could be here, it could also be there. You wouldn't know until you measure it, when it randomly decides where it wants to be. And when I mean randomly, I genuinely mean randomly. It is physically impossible to predict the location with 100% certainty. This is called a superposition, where it is in multiple positions at the same time, with this being proved by Schrödinger, who was the one that hates cats for some reason. Finally, let's look at the deepest part of physics and reality. What makes up particles in atoms? Quantum mechanics. Or what most people think quantum mechanics are anyway. Well, firstly, the electron is already its own particle. It is what's called a lepton, along with its 2 brothers, and their smaller cousins. Then there are the quarks, the up, down, charmed, strange, bottom and top quarks. And these are the particles that make up the proton and the neutron. And they are also, instead of being called types, they are called flavors. Because, tasty up quark flavored ice cream. Seriously, physicists cannot name things seriously. Like, what the Then there are the bosons. So, you know how I've been talking about all these different forces, like the electromagnetic force? Well, those aren't invisible things. They are actual particles that move and interact with reality. There is the photon, which mediates the electromagnetic force, the gluon for the strong nuclear force, and the Z and W bosons for the weak nuclear force. And then there is the Higgs boson, which is its own special thing and gives mass to particles. And why is there no gravity boson, you ask? Because clearly gravity is a force. We haven't found it yet. That is literally the biggest question in physics right now. So if you find it, you get a Nobel Prize. And all these particles together make up the standard model of physics, which is our best idea of the universe along with general relativity. Except there is also a negative version of all these particles, so there's that as well. And that should be all of physics explained with anime. If I'm being honest, this was incredibly hard to explain, though mainly because I am trying to explain it with anime, and that makes no sense already, so trying to explain physics with it is ridiculous. Anyway, if this video ends up doing well, maybe I'll try explaining another area of science with anime girls. I swear, if this actually gets shown in someone's classroom,